Finishing out the chapter 9, Counting and Probability, starting with Pascal's formula and the binomial theorem. In this section, we derive several formulas for the value of n choose r. The most important is Pascal's formula, which is the basis for Pascal's triangle and is a crucial component of one of the proofs of the binomial theorem. We offer two distinct proofs for both Pascal's formula and the binomial theorem. One of them is called algebraic because it relies to a great extent on algebraic manipulation, and the other is called combinatorial because it is based on the kind of counting arguments we have been discussing in this chapter. Now, Pascal's formula, named after the 17th century French mathematician and philosopher, is one of the most famous and useful in combinatorics, the formal term for studying counting and listing problems. It relates the value of n plus 1 choose r to the values of n choose r minus 1 and n choose r. Specifically, it says that n plus 1 choose r equals n choose r minus 1 plus n choose r, whenever n and r are positive integers with r being less than or equal to n. This formula makes it easy to compute higher combinations in terms of lower combinations. If the values of n choose r are known, then the values of n plus 1 choose r can be computed for every integer r, such that r is between 0 and n. Pascal's triangle, geometric version of Pascal's formula. Basically, to choose n plus 1 choose r, you add n choose r times plus n choose r minus 1. So it's in the triangle that is formed by r and n, plotting r and n, 10 is equal to 6 plus 4, or 10 is 4 plus 6, or 5 is 5, you get 5 for 4 plus 1. Likewise, if you were to calculate 6, it would be 10 plus 5. 6 choose 3 would be 10 plus 10, or 20. So that's how the numbers are related on the triangle. Sometimes it is simply called the arithmetic triangle because it was used for centuries before Pascal by Chinese and Persian mathematicians. But Pascal discovered it independently, and ever since 1654, when he published a treatise that explored many of its features, it has generally been known as Pascal's triangle. I just did the Pascal's triangle to compute the values of 6 choose 2 and 6 choose 3 using the values from 5 choose 1, 5 choose 2, and 5 choose 3. So, Pascal's formula, definition, formula, or Theorem 871. Let n and r be positive integers with r being less than or equal to n. Then n plus 1 choose r is equal to n choose r minus 1 plus n choose r. Use Pascal's formula to derive a formula for n plus 2 choose r in terms of values of n choose r minus 1, and n choose r minus 2. Assume that n and r are non-negative integers and r is between 2 and n inclusive. By Pascal's formula, n plus 2 choose r is equal to n plus 1 choose r minus 1 plus n plus 1 choose r. Now apply Pascal's formula to n plus 1 choose r minus 1 and n plus 1 choose r and substitute into the above to obtain this. Combining the middle two terms gives the final result for all negative numbers, all non-negative integers n and r, such that r is between 2 and n inclusive. The binomial theorem. In algebra, a sum of two terms, such as a plus b, is called a binomial. The binomial theorem gives an expression for the powers of a binomial, a plus b raised to the nth power, for each non-negative integer n and all real numbers a and b. Gives this expression here that you might remember from college algebra or algebra 2. But given it in terms of n choose k. Note that the second expression equals the first because n choose 0 is equal to 1 and n choose n is 1 for all non-negative integers n. Since b to the power of 0 is 1 and a to the n minus n is 1. So for any real number a and any non-negative integer n, the non-negative integer powers of a are as follows. A to the n is 1 if n is equal to 0. And if it's greater than 0, it's a times a to the n minus 1. So that's from basic algebra there. Expand the following expressions using the binomial theorem. We'll just look at a. A plus b to the fifth would be expanded to this summation here, which expands out with the binomial terms. And you get a to the fifth plus 5a to the fourth times b times 10 times a to the third times b to the second plus 10 times a to the second times b to the third plus 5a b to the fourth plus b to the fifth. Now observe that this is the second one. We kind of skipped that one. But now express the following sum in closed form without using a summation symbol and without using an ellipsis. And summation of k with k from 0 to n choose k times 9 to the kth power. Now it looks like the binomial theorem, the binomial expression, except for the first number. But when a number is raised, when the number 1 is raised to any power, the result is still 1. So you can insert the 1 to the n minus k into the expression, which yields, simplified back by the binomial theorem, 1 plus 9 to the n, or 10 to the n. Much simpler. And that is it for this slide deck. The second section for the day is probability axioms and expected value. Up to this point, we have calculated probabilities only for situations such as tossing a fair coin or rolling a pair of balanced dice, where the outcomes in the sample space are all equally likely. But coins are not always fair and dice are not always balanced. How is it possible to calculate probabilities for these more general situations? The following axioms were formulated by a mathematician in 1933 to provide a theoretical foundation for a far-ranging theory of probability. Let S be a sample space. A probability function P from the set of all events in S to the set of real numbers satisfies the following three axioms for all events A and B in S. The probability of A is between 0 and 1 inclusive. The probability of the empty set is equal to 0. The probability of S is 1. If A and B are disjoint, that is, the intersection of A and B is equal to null, then the probability of the union of A and B is the probability of A union B is equal to probability of A plus the probability of B. In this section, we state the axioms, derive a few consequences, and introduce the notion of expected value. Recall that a simple sample space is a set of all outcomes of a random process or experiment, and that an event is a subset of a sample space. Suppose that A and B are events in sample space S. If A and B are disjoint, could probability of A equal 0.6 and the probability of B be 0.8? The sum of all probabilities within a sample space has to equal 1. So it'd be equal to 1.4, which is greater than 1, so it would not be possible. So suppose that A is an event in a sample space S. Deduce that the probability of the complement of A is equal to 1 minus the probability of A. S representing the universal set U. A intersected with the complement of A is null. And A union A complement is S. Thus, S is the disjoint union of A and A complement. So the probability of the union of A and the complement of A is the probability of A plus the probability of the complement of A, which is equal to the probability of S, which equals to 1. So the probability of A plus the probability of the complement of A is equal to 1, and subtracting the probability of A from both sides gives the result that P is the probability of complement of A is equal to 1 minus probability of A. So the probability of the complement of an event, if A is any event in a sample space, S, then the probability of A, the complement of A, equals 1 minus the probability of A. And the probability of a general union of two events, if S is any sample of space and A and B are any events in S, then the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. And if you recall, that's very similar to the number of elements in two sets. The union of set A and B is the number of elements in A plus the number of elements in B minus the number of elements in the intersection of A and B. So they don't get counted twice. Make sense? Okay. Suppose the card is chosen at random from an ordinary 52 card deck. What is the probability that the card is a face card, Jack, Queen, or King, or is from one of the red suits? Let A and B be the event that the chosen card is a face card, and let B be the event that the chosen card is one from one of the red suits. The event that the card is a face card or is from one of the red suits is A union B. Now the number of elements in A is 4 times 3 because each of the 4 suits has 3 face cards. So P of A is equal to 12 over 52. Now the number of elements in B is equal to 26 because half the cards are red. So the probability of B is 26 over 52. Finally, the number of elements in A intersect B is 6 because there are 3 face cards in hearts and another 3 in diamonds. And so the probability of the intersection of A and B is equal to 6 over 52. And it follows from the formula for the probability of a union of any two events that the probability of the union of A and B is equal to 12 over 52 plus 26 over 52 minus 6 over 52, or 32 over 52, which equals about 61.5%. So the probability that the chosen card is a face card or is from one of the red suits is approximately 61.5%. Expected value. Suppose the outcomes of an experiment or random process are real numbers, A1, A2, A3, etc. to AN, which occur in probabilities P1, P2, P3, Pn. The expected value of the process is the summation of A sub k times B sub k, where k is 1 to n. So suppose that, in an example, suppose that 500,000 people pay $5 each to play a lottery game with the following prizes. 1 grand prize of $1 million, 10 second prizes of 1,000 each, 1,000 third prizes of 500 each, and 10,000 fourth prizes of $10 each. What is the expected value of a ticket? Each of the 500,000 lottery tickets has the same chance as any other of containing a winning lottery number. And so P of k is equal to 1 over 500,000 for each k 1 through 500,000. Let A sub I be the net gain for an individual ticket, where A1 is equal to 999,995. The net gain of the grand prize ticket, which is $1 million plus minus the $5 cost of the winning ticket. Likewise, $995 net gain for 10 second prize tickets. $495 the net gain for each of the 1,000 third prize tickets, and $5 the net gain for each of the 10,000 fourth prize tickets. Since the remaining 488,989 tickets just lose $5, those remaining values would be minus 5. The expected value of the ticket is therefore the summation of A sub k times 1 over 500,000. K is equal to 1 to 500,000. factor, you can take out the 1 over 500,000 and just have it be the summation of a sub k, where k is from 1 to 500,000. Now the values of a sub k are 999,995 for 1. For 10, it's 995. For 1,000, it's 495. For 10,000, it's 5. And for 488,989, the value is minus 5. Therefore, multiply everything out, do a little division, you get negative 178. In other words, a person who continues to play this lottery for a very long time will probably win some money occasionally, but on average will lose $1.78 per ticket, which would be how lotteries make money. So the final section of chapter 9, we have, come on, cooperate. All right. Conditional probability, Bayes formula, and independent events. Conditional probability. Let A and B be events in a sample space. If the probability of A is not equal to 0, then the conditional probability of B given A, denoted B, the probability of B bar A, is the probability of A intersect B divided by the probability of A. Now, conditional probability is kind of a, basically if A is true, what is the probability of B happening if A occurs? Okay, so like a pair of fairy dice, one blue and the other gray are rolled. What is the probability that the sum of the numbers showing face up is 8, given that both of the numbers are even? The sample space is the set of all 36 outcomes obtained from rolling 2 dice and noting the numbers showing face up on each. As in an earlier section, denote by AB the outcome of the number showing face up on the blue die as is A, and the one on the gray die is B. Let A be the event that both numbers are even, and B be the event that the sum of the numbers is 8. Now, if the set of all possible outcomes in A is given here, where both numbers in the on the 2 dice are even, the sum of if the set of combinations where the sum equals 8 are given in these combinations, are given in this set, and the intersection between the 2 sets is these 3 elements. Because the dice are fair, so all outcomes are equally likely, probability of A is 9 out of 36. Probability of B is 5 out of 36. And the probability of A intersect B is 3 out of 36. By the definition of conditional probability, the end result of if A occurs, what's the likelihood of B occurring? Would be 1 out of 3. Make sense? But A has to occur first before B is considered. If A doesn't occur, it doesn't matter what B is. It doesn't count toward the probability. Note that when both sides of the formula for conditional probability are multiplied by the probability of A formula for the probability of A intersect B is obtained. And dividing both sides of the formula by the probability of B bar A gives a formula for the probability of A. Now we get into Bayes' theorem. Thomas Bayes was an English Presbyterian minister who devoted most of his energies to mathematics. The theorem that bears his name was published posthumously in 1763. The theorem is, suppose a sample space S is a union of mutually disjoint events, B1, B2, B3, etc. And suppose A is an event in S. And also suppose A and B, both A and each B have non-zero probabilities for every integer k with k from 1 to n. Then the total probability of B sub k occurring given A is given by this formula here. So, applying this, most medical tests occasionally produce incorrect results, called false positives and false negatives. When a test is designed to determine whether a patient has a certain disease, a false positive result indicates that a patient has the disease when the patient in fact does not have the disease. A false negative indicates that a patient does not have the disease when in fact they do. So, when large-scale health screenings are performed for diseases with relatively low incidence, those who develop the screening procedures have to balance several considerations: the per-person cost of the screening, follow-up costs for further testing of false positives, and the possibility that people who have the disease will develop unwarranted confidence in the state of their health. Consider a medical test that screens for a disease found in 5 people in 1,000. Suppose that the false positive rate is 3% and the false negative result rate is 1%. So, 99% of the time, a person who has the condition tests positive for it. And 97% of the time, a person who does not have the condition tests negative for it. What is the probability that a randomly chosen person who tests positive for the disease actually has the disease? And what is the probability that a randomly chosen person who tests negative for the disease does not in fact have the disease? Consider a person chosen at random from among these screened. Let A be the event that the person tests positive for the disease. B1 be the event that the person actually has the disease. And B2, the event that the person does not have the disease. Then probability of A bar B1 equals 99%. So that is the likelihood of them being testing positive given that they actually have the disease. And the complement of that would be 0.01. Now, the probability of them testing positive and given that the person does not have the disease is 0.03, where the complement of that, where the event that the person does not test positive for the disease and they do not have the disease is 97%. Also, because 5 people in 1,000 actually have the disease, the probability of B1 is 0.005. And the probability of B2 not having the disease is 0.995. By Bayes' theorem, the probability that they actually have the disease and test positive for it, when they test positive for it, they test positive and they actually have the disease is only 14.2%. Likewise, if they test negative for the disease and they actually don't have the disease, the odds of that being the case are 99.995%. Or a negative test does not have a person with a negative test does not have the disease is 99.995%. These are fairly typical numbers of the situation where the screening test is significantly less expensive than a more accurate test for the same disease, yet produces positive results for nearly all people with the disease. Using the screening test limits the expense of unnecessarily using the more costly test to a relatively small percentage of the population being screened, while only rarely indicating that a person who has the disease is free of it. Independent events. Suppose a fair coin is tossed twice. It seems intuitively clear that the outcome of the first toss does not depend in any way on the outcome of the second toss, and vice versa. For instance, A is the event that a head is obtained on the first toss, and B is the event that the head is obtained on the second toss. Then, if the coin is tossed randomly both times, events A and B should be independent, in the sense that in the event of B, A occurs, should be the same probability as A occurring. Likewise, in the event of A occurring, B occurs, should be the same as the probability of B. Definition of independent events. If A and B are events in a sample space S, then A and B are independent if and only if the probability of A intersect B equals the probability of A times the probability of B. Let A and B be events in a sample space S, and suppose that A intersect B is null. Probability of A and the probability of B are not equal to 0. For disjoint events, intersection of A and B, the probability of the intersection of A and B, which is the null set, is not equal to probability of A and B, probability of A times A probability of B. Because probability of A intersect B is equal to 0 because the intersection is null by property axiom 2, but probability of A times probability of B is not equal to 0 because neither A nor B equals 0. Thus, for disjoint probabilities, the probability of A intersect B does not equal to the probability of A times the probability of B. Now, probabilities of intersections of two independent events. A coin is loaded so that the probability of heads is 60%. Suppose the coin is tossed twice. Although the probability of heads is greater than the probability of tails, there's no reason to believe that whether the coin lands on heads or tails on one toss will affect whether it lands heads or tails on the other toss. Thus, it is reasonable to assume that the results of the tosses are independent. What is the probability of obtaining two heads? Well, that's the two independent events, so it would be 0.6 times 0.6, or 0.36, or 36%. What is the probability of obtaining one head? Well, there's two possibilities for that, either heads first and tails second, or tails first and heads second. Either way, it's going to be 0.6 times 0.4, or 0.24 times 2, 0.48, or 48%. What is the probability of obtaining no heads? Well, that would be the probability of tails on both, which is 0.4, times 0.4 would be 0.16, 16%. What is the probability of obtaining at least one head? Well, the easiest way to calculate that, given that we just calculated the probability of obtaining no heads, is to take the complement of that. The complement of obtaining no heads is the probability that you have at least one heads. So 1 minus 0.16, or 0.84, 84%. Sample space S consists of 4 outcomes, which are not equally likely. Let E be the event that a head is obtained on the first toss, and let F be the event that the head is obtained on the second toss. Probability of E and the probability of F both equal 0.6, and it is to be assumed that E and F are independent. The event of obtaining two heads is E intersect F, and because E and F are independent, two heads, probability of two heads equals P probability of E times the probability of F, or 0.6 times 0.6, or 0.36, 36%. Likewise, I went through this on the previous slide. Two mutually exclusive ways: heads first, tails second, or tails first and heads second, equals 0.48%, or 0.48, or 48%. No heads. Probability of the complement of E and the probability of the complement of F, 0.4 times 0.4, 0.16, or 16%. Now they do the two ways of solving the fourth one. Both yield 84%. I went with the second way, where the event of obtaining at least one head is complement of the event of obtaining no heads. Now suppose coin is loaded with the probability of heads being 0.6%, or 0.6, and suppose that the coin toss is tossed twice. If this experiment is repeated many times, what is the expected value of the number of heads? Think of the outcomes of the coin tosses as just 0, 1, 2, 0, 1, and 2. The probabilities of these outcomes are 0.16, 0.48, and 0.36 respectively. Thus, by definition of the expected value, there's the probability of 0 would be 0.16, probability of 1 would be 0.48, and the probability of 2 would be 0.36. So the total number of heads you would expect over time to be 1.2, or out of 100, 60 heads. 4 conditions must be included in the definition of independence for 3 events. Let A and B and C be events in sample space S. A, B, and C are pairwise independent if and only if they satisfy conditions 1 through 3 below. They are mutually independent if and only if they satisfy all 4 conditions below. These are similar to what we saw earlier, just expanded out, and all the permutations. The definition of mutual independence for any collection of n events with n greater than or equal to 2 generalizes the 2 definitions given previously. Events A, 1, 2, 3 to n in a sample space S are mutually independent if and only if the probability of the intersection of any subset of these events is the product of the probabilities of the events in the subset. So, taking it out further, a coin is loaded so that the probability of heads is 0.6. Suppose the coin is tossed 10 times. It is reasonable to assume that the results of the tosses, of course, are mutually independent. What is the probability of obtaining 8 heads? What is the probability of obtaining at least 8 heads? For each I, 1 through 10, let HI be the event that a head is obtained on the ith toss, and let T sub I be the event that a tail is obtained on the ith toss. Suppose that the 8 heads occur on the first 8 tosses and the remaining 2 tosses are tails. This is the event. For simplicity, they abbreviate it this way. By definition of mutually independent events, the probability of this combination coming up is obtained by multiplying this out. Because of the commutative law for multiplication, if the 8 heads occur on any other of the 10 tosses, the same number is obtained. For instance, this combination here yields the same as here. Now, there are as many different ways to obtain 8 heads and 10 tosses as there are subsets of 8 elements that can be chosen from a set of 10 elements. This number is 10 choose 8. It follows that because the different ways of obtaining the 8 heads are all mutually exclusive. So the probability of 8 heads would be 10 choose 8 times 0.6 to the 8th times 0.4 to the 2nd. But they don't multiply it out and give a result in percentages. Kind of a Missing point on the slide there. By reasoning similar to that in part A, 9 heads would be the number of different ways 9 heads can be obtained in 10 tosses, times 0.6 times to the 9th power, times 0.4 to the 1st power. Or 10 choose 9. 10 heads is the same way. Number of different ways 10 heads can be obtained in 10 tosses, which is only 1, times 0.6 to the 10th, times 0.4 to the 0th. Because obtaining 8, obtaining 9, and obtaining 10s are mutually disjoint events, the probability of getting at least 8 heads is the sum of those 3 probabilities. Again, they do give this final result being 16% chance, 16.7% chance of that happening. Independent events. Just kind of throwing this out here. Probabilities of the form given here, where p is between 0 and 1, are called binomial probabilities. No elaboration, no where is this used, just throwing it out there because that is it for the slides for today.